Hello, everyone, and welcome to our webinar on evaluation of interramp slopes using a discrete fracture network-based method. My name is Marisol Valerio. I'm a principal rock mechanics engineer at WSP, and I'll be moderating today's webinar. The webinar will present a discrete fracture network-based approach that has been developed by WSP to identify multi-bend scale rock blocks in open pit slopes and evaluate their stability using a 3D probability of failure solution. This work builds on our paper that we originally presented at the Slope Stability 2020 conference, and you can download a PDF of this paper in the handout section of the GoToWebinar control panel. Our presentation today will be about 30 minutes long, and it will be recorded, and a link to the recording will be provided after the webinar. If you have any questions during the presentation, please submit them through the questions box of the GoToWebinar control panel, and we'll have about 15 minutes at the end to go over questions. So with that, it's my great honor to introduce to you our presenter, Dr. Steve Rogers. Steve is a senior principal geoscientist and rock mechanics consultant with WSP, who has been using DFN methods for characterizing fractured rocks and reservoirs for over 20 years. Over to you, Steve.
Great, Marisol. Can you just confirm you can hear me?
Yes, we can hear you.
Brilliant. I say good morning or good afternoon, good evening to you, wherever you're watching. Anyway, thank you so much for giving up some of your valuable time, and very excited to be able to talk to you today about some of the work that we've been doing over these last few years, trying to embed discrete fracture network thinking into how we evaluate interamp scale slopes. Just want to start by actually apologizing for some reason I can't mute WhatsApp notifications. So it's possible my children might send me a message at some point during the presentation, so I apologize for that. What we're going to be talking about today is we can start off by just looking at some of the issues around interamp design approaches, how we can use discrete fracture network modeling as part of that, as part of addressing this problem, how we identify wedges and blocks in the slopes, and then how we evaluate their stability of these, particularly non-daylighting wedges, how we use the results of this for looking at interamp slope designs, and then finishing off looking at more wall scale analysis and testing property sensitivities, and then some final thoughts. Before I go any further, I should just say I'm just the front guy today. I represent a team of people, many a lot smarter than me, who came up with ideas and developed code and tested and implemented, and so just want to acknowledge a range of both women and men, and young and old, and geoscientists and engineers and developers involved with the work that we're going to talk about today. Obviously, myself and Marisol, we work for the mining team at WSP, which is worth just stressing, over 5,000 dedicated mining staff sitting within the WSP company of nearly 70,000 people. So whether you're working in terms of resource definition and resource modeling, I should actually just also give a big plug for my colleague Graham Banks and his critical mineral initiative. But so whether we're talking resource geology all the way through to front-end studies, design, engineering, construction, and ultimately closure, WSP Mining's got skilled practitioners who can help you with those problems. So anyway, let's just think about the interamp design in a structured rock mass. So before we start, I should actually just say, so there was actually one of the questions in the pre-chat about does this approach work for all slopes? And so we're really thinking today about slopes with a kind of medium to strong rock mass and strongly structured. If you've just got a weak rock mass, we don't really need the structures, and there's far more simple approaches for how we can look at stability. But really, we're thinking today about those rock masses that are where stability is either structurally controlled, perhaps more likely it's controlled by composite mechanisms that involve both structures and rock mass playing roles within failure. So it's important to think about, how we capture the structure within our analysis and our modeling, when there's often actually too many structures to discretely kind of handle. So this little graph in the middle of your screen represents, at the bottom, it's kind of the trace length of structures against cumulative count. So we know we have a relatively small number of very large structures. There you go, 10 kilometers. It'll take a very large pit to be seeing these structures. But we always, on a log scale, we have, millions, tens, hundreds of millions of very, very small structures. So we know at the large scale, these are large faults that are, hundreds of meters or more. We've seen them, we can map them, we can wireframe them. But obviously, as we become smaller, they're becoming more and more numerous. So we might know them and have mapped them, but not wireframe them. We might not even know about them. So these are some of the challenges we have to, we're trying to unpack a little bit today, in terms of how can we actually try and represent a structure that we know is there, but perhaps is, it's kind of hard to explicitly represent. And in particular, how do we manage a lot of the uncertainty around that, that sort of structural fabric? Now, in terms of how we currently address inter-ramp slope designs, really there's 4 broad methods, and they all have advantages and disadvantages, and I'm not going to dwell too much on those in particular, but obviously, just to summarize, we have just simple kinematic methods like something like S-wedge. I'm sure many people have used, for simple effectively computing the kinematics on a wedge. We have limit equilibrium solutions in 2D or 3D, very fast, but perhaps not so good at handling a fabric. We obviously have some amazing numerical codes, and some wonderful modeling is done with codes like FLAC 3D or 3DEC, with 3DEC embedding major structures. And of course, we have some DFN based methods, something that I myself have been very familiar with, but there's no one perfect solution, and that's really where we're starting from today. So we were motivated to try to find an efficient approach that would actually allow us to perform both back analysis or forward predictive results in a timely manner, knowing that some of the more heavyweight codes would struggle in that area. So what we're looking for is a method that allows us to handle that structural complexity, that allows us to consider both a structural and rock mass component, to be able to sweep through a range of different property sensitivities. We want something that's probabilistic, so we want to be able to run it lots of times in short run times. So that's really some of the motivations behind this code that we call 3D POF. And we want to achieve this quickly so that we can actually aid in solving operational issues, help develop mitigation efforts where necessary, of course, evaluate true slope risk. So that's a little bit of background to FRACMAN and the DFN 3D POF solution. But let me just start, first of all, by just, for those people who are perhaps less familiar with discrete fracture network modeling, let's just give you a little bit of background to that. So the idea in DFN modeling is we're going to explicitly represent critical structure. So what we're going to do is we're going to transform geological and geotechnical information into quantitative parameters that describe our fracture network, and with the aim being to try and generate geologically realistic DFN models, of our data that we can then analyze. It's a stochastic process, which basically means the properties are going to be drawn from distributions of, whether that's orientation. So obviously we don't draw from a histogram like here. That's, yes, it's a stereonet, but we draw from a histogram or some kind of distribution of size and intensity. I've actually noted at the top right, we could also have on those structures, we can actually have distributions of properties like cohesion or friction angle, permeability, stiffness, whatever we want. But these aren't critical properties. The main properties that we need to define for our DFN model are fracture orientation, size, intensity, and spatial variation. And we kind of do that either on a sort of family by family basis, or perhaps all together. It just kind of really depends on the application. If we just look at this little example on the right, imagine we have a slope, a stack of benches. We have some borehole data that's giving us an intensity of structures seen in the borehole. Maybe there's a televiewer log, so we have some orientation, and mapping on the benches gives us some size of structures. So in essence, what we would do to build a DFN model of this little slope, we would start by maybe embedding any deterministic structures. There's a major structure running up these through this stack of benches there, and then we just stochastically add that fabric of structures. And remembering, because it's a stochastic process, we can carry out a probabilistic assessment. So we can build these models, hundreds of thousands of times if necessary, with each realization being equiprobable, and then we can look at the distribution of results at the end. Now, lots of people will be familiar with DFN modeling of old, which was very simple in many ways. Is what I would have called the sort of crack in the box approach, where we just put DFN fracture objects into a volume. Of course, now DFN modeling is a far more geomodeling based approach, where we actually have the ability to model much more complex fracture architectures. So just considering some of these cartoons on the left, we have the sort of homogeneous model, which is kind of, we might consider that's the crack in the box, but now we have the tools and the techniques to be able to model these ordered layer bound systems where the orientation of joints is driven by the bed thickness or the bed heights. We have deformed system with lots of folding or faulting and clustering. So there's a range of different fracture architecture styles that we can incorporate into those models. And we want to make sure, I'm a pragmatist, so simplicity comes first. But if the particular geology of the slope requires it, we have the tools to do that. Just a couple of examples on the right. Very layer bound jointing system with then through going shear fractures up in the top right, and then the image on the bottom right actually shows how bedding faults have been simulated to actually follow the limestone beds that you can just see in light blue. So the trend of the actual simulated bedding faults is just actually moving through space as it follows those beds. Okay, just a quick look for those people who've perhaps never seen FracMan before. FracMan is a software developed from within WSP, probably the premier and certainly the initial, the first commercial DFN code available in the marketplace. And please do reach out if you'd like to know a little bit more about that. And my contact details are at the end of this presentation. If you apologize for, oh gosh, it's all going wrong. Thank you. Anyway, so let's think about how we might build a DFN for a slope. So here's just a typical slope. We've got some mapped faults. So that's a starting point. That leads us to wireframe fault objects. So they'll be included as deterministic features. Perhaps we have some photogrammetry, bench or cell mapping. That's going to give us some length scale data, perhaps some orientation, even some intensity. So that's where we can get some data there. In terms of the actual, when we look at the size of structures, we do find that whilst cell mapping or photogrammetry on a bench scale is useful, we need to think at scales of more like tens and hundreds of meters. And we actually find power law analysis is a very good way of being able to tie this together. This graph here shows, again, the similar graph to the cartoon I showed you at the beginning. It's structural length on the bottom against cumulative count on the side. So we actually find here, so what I put number 3, this is actually the large pit scale structures. Number 2 represents cell mapping within a section of the slope, and down right here at the top, that's actually underground mapping. So actually find this common size trend that we can use in modeling structures within the slope. We'll have some boreholes, so geotechnical logs. We're going to give us and intensity of structures. So this is how we kind of put our information together to, you know, at a kind of general scale, sort of how we sort of model that slope. And I'll look at later just some of the ways perhaps we can add a little bit of complexity into that. Now, when we're thinking specifically about interramp analysis, we're sort of thinking about a stack of benches and, you know, what is an appropriate interramp slope angle that we can support for that. So just to take you through that sort of workflow. So imagine, you know, on the left, that's our data, just like we just saw on the previous slide. And we're going to build a DFN model in a volume. Think of this in a way, this is what you might call an ex situ model. So it's not necessarily exactly in the space of the slope, because really what we want is a slope object that we can modify easily to test a variety of configurations. And so we build this ex situ model with, in this case, there were 3 different fault trends. This is actually some work that's talked about in the paper, that please do download a copy. So this was from Bingham Canyon. There was 3 different fault trends, these bedding, normal, and fissure trends. So we build up this DFN model of these different components, and then we search through the DFN, and we identify blocks that are forming on this, you know, behind the slope. You can just see these large green multi-bench scale blocks. So green means stable and red is unstable, and we'll just look in a little bit more detail about what that means. But this is the process: data analysis and characterization, DFN model generation, and then block identification. When we look in a little bit more detail at the blocks that are actually forming on the slope, we kind of see 3 broad types of blocks. So we've got up here in the top left, just a simple 1 to 2 bench, it's a simple wedge. In this particular case, it's kinematically stable. Down here in the bottom right, there's B. It's a 1 to 2 bench simple wedge, and that's kinematically unstable. But what we're really interested in is these large multi-bench volumes, what effectively are non-daylighting wedges. So they're wedges that are nearly always kinematically stable, because the shape of them means them moving is not kinematically easy. It's not just a simple calculating sliding resistance. They're usually held stable because they're sitting behind a buttress of rock mass at the toe of the slope, or perhaps laterally, or even just the overall shape of the wedge means maybe it's like an hourglass. The shape means it doesn't want to move. And really, so it's evaluating the stability of these non-daylighting wedges at the heart of the 3D POV approach. So that's, you know, dig even deeper into one particular wedge. So here we actually have a non-daylighting wedge. It's about 140 meters long in total. About covers five benches, and you'll see on this figure here, the red lines actually represent the trace of major structures on the slope. So you actually see that it's partially formed by these major structures, but the blue and kind of green smaller fractures represent the stochastic fabric that we've added, in this particular case constrained from borehole data. So you'll understand, and what we've really learned over these last few years is that these large non-daylighting wedges are typically defined by this combination of major structures and intermediate structures. Major structures on their own often don't fully enclose the volume, and we really need this other fabric. Now, if we look at this particular wedge from the side, you actually see, so it, you know, when we look down, it kind of looks like it just wants to come out, but you'll actually see it's sitting behind this buttress of rock mass. So therefore, any failure, if that block wants to move, it's going to have to involve both some kinematic sliding and failure of that rock mass buttress, and that's what 3D POV is actually going to compute. So for every block, we're actually going to look about how we're going to calculate the factor of safety of that wedge, considering both the sliding kind of component, and also the failure of the rock mass. In this particular case, that's which I've turned off the rock mass, but that's is going to have to fail through this buttress. How 3D POV actually looks at that, let me dig in a little bit deeper. So we generate, let's say on a sector scale model, we'll run 100 realizations. We'll be generating somewhere between tens, even hundreds of thousands of these blocks in FRAPMAN, and they're taken into 3D POV, and it's going to compute the factor of safety considering joint and rock mass and pore pressure inputs. Now, of course, how we compute that is very simple for us. If we were just looking at a relatively simple wedge, but for more complex wedges, we actually have to consider a variety of different potential failure pathways. So let's just look at this block here. So in the image we have here in the bottom right, it's a more complicated shaped block here, taken in sections. So you actually see here's a bedding faults is actually sitting on, and it's actually comprised also a number of other structures within it. So how we might evaluate the stability of that particular block is, so an initial one might be here. So we might just consider this as a kinematic block. We'll calculate the factor of safety. We might consider it including the toe and then this rock mass buttress at the bottom. So custom slip surface is within the code is taking the block to daylight out, and then that's how we define the rock mass component and compute the factor of safety. We might actually take this small part of the block at the top, and again with this small buttress, and then lastly, it also has the ability to consider, effectively, we'll call them notches, but if there's sort of topography in the basal plane, we're handling that. So 3D POV is stepping through these sort of potentially hundreds of thousands of blocks, and running multiple scenarios to generate this large database of factors of safety as a function of different input properties. So of course, when we run these analyses for each block, we don't just want to run it once and throw it away. One of the things we said right at the beginning is we really want to be able to consider a whole range of property sensitivities. And so this is what 3D POV does. We set up a table of scenarios we want to test. Perhaps we want to test base case rock mass strengths and some lower bound strengths, some low friction angle joint strength, some cohesionless cases. And in addition to all of those, we will always sweep through a full range of pore pressure conditions. Now, we use this term RU. For those people that aren't familiar, RU is effectively the ratio of the weight of water to the weight of rock. So an RU of 0.4 effectively is hydrostatic conditions, or approximately 0.4. Obviously, not all rock has got a weight of 2,500, a density of 2,500 kilograms per meter cube. So, but if we look at this particular case here, so this wedge here with an RU of 0, so dry conditions, has a factor of safety of 2, and as the RU increases, we see the factor of safety falling all the way down to when here an RU of 0.2, we got a factor of safety of 0.6. So here we actually see all of the results. The big dots just represent these cases shown above. Clearly, emphasizing how important water management is within slopes, with so many instabilities being primarily driven by, or certainly triggered by, high rainfall events, or the loss of water management and ponding water forming on slopes. Okay, so how do we actually use this within the actual design process? So remember, we're going to build our DFN model. We're then going to take the blocks and we're going to calculate the factor of safety for all these blocks. And we're going to then repeat this for a range of interramp angles and slope orientations. And then based on those results for each one of the designs, we can calculate the probability of failure that we take as the volume of unstable blocks divided by the volume of all blocks. And then the results from these can be compiled into these design charts where we have interamp angle on the base against the probability of failure. And there we have the two DAC lines of a 10% or a 5% POF drawn on the graph. Okay, so that's, it's actually pretty simple. It's really about the DFN model, then generating the blocks, evaluating the stability of the blocks, and then looking at, the volume or the tonnage of potential instability for different designs, and then coming up with a probability of failure criteria. Of course, that's a simple sector scale model. As I said, that was really ex situ. It doesn't have to be in the real world, so to speak. But here we can also build a model scale result, and that's really important because obviously the sector scale models will give us help in defining appropriate interamp angles for a sector. But we really need a way to test the final design. And in particular, we have to look at what's actually happening at sector boundaries. Sector boundaries are so often defined by major structures or these contacts, faults, dikes, change in lithology. So often lots of interesting things, and I'm going to say interesting, unfavorably exciting events. And so we want to build the same, take the same general approach, but this time we're going to build it on a kind of wall scale analysis. The model there actually again is related to the paper from the south wall of Bingham. There's kind of 5 broad geotechnical domains there. The models are, 100 realizations of those models are run. And I'll just look in a moment at how we process that. Now, this particular model, the properties for each domain are defined independently. So for each domain, there's a sort of an orientation, intensity, and size. But we can actually add a little bit more complexity where we have data to support it. This example underneath, which is actually from Chucky Kamata, we actually found that the intensity of smaller intermediate scale faults was strongly conditioned and controlled by the distance to the major wireframe structures. So in this particular case, we actually could generate a distance to fault property such that we could then build the DFN on the right, where it's not so easy to see, but the smaller stochastic faults are in blue. Their intensity is controlled by the distance to the black major structures, and you actually see this graph on the left where the red represent actually measured fault intensity from boreholes, and the blue represents the intensity of simulated faults. So there's an example where we've added an extra geological control into the DFN at the scale of the wall. Now, how we actually process those results is we actually aggregate all the results from the different, say, 100 realizations and compile the results into a grid on the slope. So in this particular case, what I'm just showing is the block count. So in each cell, the hot spots represent areas where blocks are more likely forming. So think about this as a way of looking at the probability of occurrence of blocks. Some other properties that we use, common one is block failure percentage, which is really like a kind of pseudo probability of failure, because what we're looking at is the count of failing blocks in a cell divided by the count of total number of blocks in the cell. So there's a variety of things we can do. And in fact, we're just completing a study at the moment where the correlation between high block failure percent and historic failures, is just amazing. It's just had me purring for the last couple of weeks. Big shout out to the team for that. Of course, as I said, even at the wall scale, we can also be running sensitivity. So this example is for a pit where we actually ran a whole range of different sensitivities for each sector. And let's just look at the graph on the right. This effectively represents failure volume, average unstable failure volume against pore pressure for 4 different scenario. So as a base case scenario, that's this sort of orange line on the right. Green is a low discontinuity strength. The kind of purple is a low rock mass strength, and the blue is a low discontinuity rock mass strength. And you can just see going from those cases, we go from a relatively low failure volume to much higher failure volume, with the increase in pore pressure clearly, you know, driving instability in all of those cases. The red line, however, represented the approximate failure tonnage observed in that sector. So we actually see which one of these scenarios is actually best matching the observations. Now, if we actually look at what this kind of means in terms of the actual 3D POV results, the image here on the bottom left is showing all of the unstable wedges forming for the low rock mass strength case. That was the purple line with an RU of 0.2. So you actually see on this southern part of the pit, very, you know, a high number of unstable wedges forming. Whereas actually, when we look at it's the same DFN model, but with the low. This one is the low discontinuity strength and an RU of 0.2 again. It's a much stronger case, and you see that's the difference between the green line here, where we got not a lot of failure, compared to the this kind of purple line, much more failure. So it's just a great way to be able to identify critical controls on sector slope performance. Okay, so we're just about at time. I mean, just some takeaways for you is, and I think DFN modeling, it's a wonderful way to provide a structurally sensible approach to capture structure and embed it into our analysis. Because of the fact it allows us to add this scale of structures that we know are there and we know are important, yet perhaps too numerous to actually include explicitly as wireframed objects. And we're using kind of some underlying geology and fracture modeling techniques to, you know, efficiently geomodel that fabric, rather than just to put it in as some implicit structure. And then we can consider the interaction between those different structures, and using the kinematics to effectively assess the block formation within the slope, and think about also the probability of occurrence. This is really important. We want to get away from this idea of the possibility of occurrence and think about the probability of occurrence. Then 3D POV is then processing those blocks, you know, to actually identify the factor of safety, and considering this composite failure mechanism of both, you know, sliding and rock mass failure, including property sweeping through all of these different parameters. And then, you know, we've successfully applied this technique at a number of pits where we've been looking at interramp designs, back analysis of multi-bench failures, and then front-end evaluation of potential pit scale instabilities relatively to more greenfield sites, as well as sector hazard ranking and failure tonnage calibration. So this, honestly, I think this is the part of my career that I've been the most proud to be involved with, and I hope a little bit of that excitement has come across today. I'm going to hand back to Marisol, who's going to just moderate a few questions that you might have asked. I hope you've asked something, and but please do get in touch with us if you want to know more, and her contact details are here. So thanks, Marisol. Let me hand it back to you.
Wonderful. Thanks, Steve, for a really great presentation. Once again, if anyone would like some more details on the DFN methods that Steve just described, please download our paper. It's available in the handout section of the GoToWebinar panel. So we'll now move into the questions portion of the webinar. If anyone has any additional questions, as we're going over the ones that have already been submitted, please continue to enter them into the questions box. So Steve, the first question we have here is, does the DFN 3D POF approach for pit slope design require additional data collection, for example, Do you need to drill many more holes to get a reliable model for the pit conditions to use this approach?
That's a great question, Marisol. Thanks very much to whoever sent that one in. So the answer is no. Just your conventional site investigation data typically provides the data we need. Often we do find having guiding that data acquisition a little provides better results. An example might be, for instance, the interpretation of photogrammetry. Encouraging the interpretation to be looked at with a little bit more of a squinted eye, so that we're looking for structures that are running over 2 or 3 or 4 benches, a little bit more relevant rather than just focusing on perhaps structures at one bench. So that's an example, perhaps, how we might just say, well, it's a slight modification of the data acquisition rather than new data in particular. But certainly not a particular need to drill just to drill more boreholes, no.
Thanks, Steve. Another question's coming through here. Once you have all of your input data, how long do these DFN models typically take to build and run?
Ooh, that's always the million-dollar question. So, assuming that we've gone through the characterization phase and we actually have the inputs to put the models together, I mean, a sector scale models actually usually just take a few days to kind of just to set up, but the actual run times are very quick. So to run, let's say, a particular sector model where we're going to sweep through a variety of different slope angles and orientations, and then run through 3D POV, it's usually the order of a few days. But it's just running away the DFN part and then the 3D POV part. So it's actually pretty quick, but that's running a very large number of scenarios in one go. So it's not like it's running once for 3 days. It's actually effectively generating hundreds of models and then running hundreds of thousands of factor of safety calculations in 2 to 3 days.
Thanks, Steve. Another question here that comes up a lot. At what stage can you apply this approach? Since fracture lengths are critical, a project with only oriented core and no face mapping would present a problem, or do you still try to model at these early stages?
Yeah, actually, that's another good question. We've actually did one of the applications that we've actually used the sort of DFN 3D POV approach for was a sort of almost a greenfield site. It was a pit in development, so it had a reasonably robust sort of structural model, and we but obviously limited amount of data. But what we did was we could actually take that structural concept to actually be able to test some particular DFN styles, and in terms of particularly thinking about the question of length, we could use used some relationships to the actual mapped structure lengths and to the large structures, as well as some analog data. And of course, because this is modeling, we can easily test a variety of scenarios. So obviously we've got a growing database of observations on typical lengths of structures, and there's also lots in the literature. So we could sort of say, well, that's what is the impact of testing if we have relatively short, intermediate length, or even long lengths. So that's one of the things we can actually do, because it's a modeling approach that we can try a variety of different scenarios very quickly. So even at that early stage, we can try and identify perhaps are there any critical geometries, and also and what are the perhaps the triggering properties that might result in those critical geometries. And that helps us to guide the data acquisition such that perhaps we can accelerate certain data acquisition requirements and needs.
Thanks, Steve. Another question we have here, is there a standard minimum structure size below which you tend to omit from the inputs?
There's someone who understands discrete modeling. all discrete modeling needs to have some minimum size. So really it depends on the scale of the problem you're looking at. If you were, say, analyzing a relatively small stack of benches, let's say, you know, 3 or 4 or 5 benches, you know, you might be only looking at 100 meters. You might say, well, you know, we really don't want to even think about structures less than, you know, half a bench. Maybe if we're looking at an entire wall scale model, we might increase that minimum size that we don't look at. So to some extent, it's very much driven by the scale of the problem, and a requirement to make the problem tractable. So yes, we have to be a little bit nimble about how we modify that minimum size, recognizing also that when we modify that minimum size, we actually have to accommodate some changes in the overall intensity, because imagine if we're not modeling below a certain size, that means we have to make sure that the intensity measurement that we've seen in the fields, which did capture those, is adjusted. And we have some well-worked methodologies for those corrections. But yeah, great question. You know, don't model the structures that aren't important, because that just wastes lots of computational time and loss of hair in terms of trying to get those models to run.
Thanks, Steve. This next one is interesting. So we've been talking a lot about open pit slopes in this presentation. Can the same method be applied to underground excavation stability assessments?
Yeah, that's a hard question. I mean, in some ways, yes. Obviously, underground excavation stability is a combination of perhaps some kinematics, but much more complex stress interactions, and increasingly with, you know, deeper and more massive rock masses, much more of a brittle failure mechanism. So if the mechanism by which stability, the stability was primarily a combination of either kinematics, that's easily handled by the DFN analysis, or perhaps, you know, just some slightly complex block shapes, which meant simple kinematics didn't apply, then, you know, then maybe 3D POV could help. But obviously, very quickly you'd find you've moved out of the range of scenarios where it would be applicable into scenarios where really you need much more complex stress analysis than is provided by this approach.
Thanks, Steve. We have a question here regarding validation. Have any validation studies been carried out comparing DFN results to a simple kinematic analysis for a single block?
Okay, well, I'm going to answer that in 2 ways. So the answer is yes. We actually have published 1 or 2 papers where I think certainly ARMA 2020, there's a ARMA 2020, there's a validation between simple kind of wedge analysis on a block and the DFN solution. And we've also done the same for planar failure. So we have actually validated the method for the single block in terms of simple kinematics. In terms of 3D POV, what we've also done is we actually took a number of blocks that were identified and the factors of safety computed in 3D POV, and actually took those into FLAC 3D and then validated them, and showed that we're getting reasonable results in terms of the more sort of rigorous computational assessment of FLAC 3D versus the very rapid linear equilibrium solution that is 3D POV.
All right, so we're over our 15 minutes here, but lots of other good questions coming in. So we'll just keep going for a few more minutes so that we can answer some of these. We have one here. It's a bit more general. What's the benefit of the DFN method over other methods?
Oh, well, I mean, obviously I've got declared self-interest, so I have to be a little bit careful about answering that. I think one of the clear values of the DFN method is that we're trying to just be a little bit more realistic. A rich man once asked a scientist to give him an accurate result, an accurate prediction of a horse race, and the scientist said, you know, I can give you 100% guarantee of predicting the horse that will win, but I'm going to model the horse as a perfect sphere in a total vacuum. And really what we're trying to do is, you know, there's a lot of the analysis techniques were developed in many ways 40 or 50 years ago, sort of simplified fabric down because they couldn't handle the computational needs. So, you know, we think about ubiquitous joints and infinite fractures, and really what we're trying to say now is, look, we've got the tools and we've got the computational power to be able to more accurately and realistically describe our rock fracture system. And if we sacrifice if we sacrifice that sort of homogenization and actually be a little bit more realistic, then we can, and actually by adding realism, then we don't have to be quite as conservative. You know, conservatism by definition is a way of trying to, you know, account for the fact that we don't really capture the system very well. And so if we capture the system better, then perhaps we can even be a little bit more aggressive in terms of our designs. But certainly we're trying to actually capture the rock mass and then model it as it is and how it behaves, rather than just as an approximation, the perfect sphere in the total vacuum.
Thanks, Steve. All right, I think we'll end with one question that seems to have come up quite a bit here. So our very last question here is, can the DFN approach also be used for bench scale analysis and design?
Yeah, great last question. And the answer is, of course, yes. We don't really necessarily need the 3D POV part for just a simple bench design, because it is primarily a simple kinematic solution we're looking for. However, what we have shown is that by switching from a sort of a simple conventional kinematic solution to a DFM one, where we're actually considering the probability of occurrence and the probability of failure of realistic blocks, rather than just these kind of assumed possibilistic blocks, I often call them, from more conventional analysis, we actually find we can actually support slightly steeper bench face angles at exactly the same kind of percentile of confidence in terms of if we were to carry out, say, a conventional CFA analysis. So the DFN solution it's there, it's more realistic, it captures the system. Think also about planar failure analysis, where, you know, the DFN, the wedge will only fail if we actually make a planar wedge. So we actually have to have lateral release planes as well as a basal surface. So, you know, again, that will give you a much more realistic and reliable prediction. Of course, we can actually take that scale of that bench scale analysis up a little bit larger to maybe, you know, 2 or 3 benches, and then we might add the 3D POV component, because then we might be starting to get a little bit of a rock mass component. And of course, in 3D POV, we can also add ground support. So perhaps if you have a particularly high value slope that actually needs bolting, we can even add that in. So again, it's another angle or facet of kind of bench design, perhaps more complex bench design. But yes, whether it's just a plain simple DFN or the combined DFN 3D POV solution, it can easily be done.
Wonderful. Thank you, Steve. Okay, well, that concludes our webinar for today. There were some questions that we didn't get to. Definitely invite you to send your comments and other questions to us after. Thanks again, everyone, for joining us today. A link to the presentation recording will be provided after the webinar later today. And if you have any other questions or you'd like to learn more about how these DFN methods could be used at your site, please do reach out to Steve or myself. We'd love to hear from you. Thanks again, and have a lovely rest of your day.